In the previous example, a single output file was created, with the contributions from each emission time as an array element in the output file. In this example, each emission period is its own independent calculation with its own output file. The results can still be organized in matrix form, such that we represent each emission time as a row and the concentration grid as a column. Then the column sum over all rows represents the total calculated concentration for all emissions. That is a conventional concentration map, while the row sum represents the contribution of that emission period to each output time. The transfer coefficient matrix represents the fractional contribution, when using a unit source emission rate, of each emission time to each output time. We can multiply the coefficient values for each row by a source term at that emission time to obtain the calculated air concentration and deposition values. Multiple source term scenarios can be investigated without rerunning the dispersion model. One advantage of the multi-file approach compared with the single-file approach is that multiple computational species can be defined. Therefore, when post-processing the emissions, one can, for instance, select either a gaseous or particulate radionuclide, because each can be associated with its own computational counterpart. Except for the new script, tcm_file, the input files required for this simulation are the same as the previous example. In the script, the particle release rates in the namelist file is the same, but the maximum size of the particle array is reduced to 10,000, because only particles from one 3-hour period will be followed in the simulation. Although not applicable in this example, lower memory requirements permit more simulations in a multi-CPU shared memory computational environment. The control file is created dynamically within the script's day-hour loop, where the start time, run duration, and output file name are created for each iteration. The model is run with a 3-hour emission period, and each subsequent simulation starts 3 hours later and has a simulation duration of 3 hours less than the previous one. All simulations have a unique output file name, where the name indicates the start time of the emission, tg_month, day, hour. Now go ahead and execute the tcm_file script. After HighSplit completes, continue with the post-processing and graphics. 2 post-processing steps were executed prior to creating the same graphics as in previous examples. In the first step, con decay, each file's concentrations are multiplied by the emission rate and decay is applied for the selected species. Most of the command line arguments are self-explanatory except for the first, in which columns in the emission file are associated with the pollutant index in the HighSplit TG file. In this example, there are 4 fields separated by colons. The first one identifies the emission column number in the cfactors.txt file. The second one is the pollutant species index in the TG file. The third field is that species half-life, and the last field is the 4-character label assigned to that species in the DG output file. More complicated applications of con decay will be shown in a later example, but for now it is sufficient to know that one can generate multiple pollutants in the DG output file from a single computational species in the TG file by having multiple groups of these colon-separated fields on the command line. In the second step, conmerge is used to merge the DG concentration files for each release period into a single file, fdnpp.bin, by matching output time periods. Unlike the con-decay program, which uses the time periods in the emission file to determine which TG files to open, conmerge uses a file, merge_list.txt, which contains a list of file names to read. The remaining graphics processing, which includes the dose conversions, are identical to the previous examples, and the results, although not identical, are very similar. Differences, as noted before, are primarily introduced by using a too low particle number release rate to speed up the calculations for these example cases. In the multi-file TCM approach, we can define multiple species in the same simulation. For instance, a non-depositing gas, a depositing gas, and perhaps a small particle. Each species has its own deposition characteristics. These computational species could be associated with different radionuclides in the post-processing step. Also, as the release time simulations are independent of each other, so they can easily be run in a multi-CPU environment. Although multiple species can be run this way, the dose computation is still limited to one radionuclide. This will be addressed in an upcoming example. In the next example, we will deconstruct the multi-file approach from one file per emission period to one file per emission and sampling period.